In this pair of videos, we're going to connect some different things together, either from before in previous units or from this unit. So in this first video, we're going to connect two things from different units. All right, it's called the fundamental theorem part 1. So here's what the theorem says. If we have this continuous function over some interval, and the function f of x is defined by this. So the function f of x is our x value is kind of the end bound for some area. So maybe we have this function, and we start out with this area. That would be like the first value for our function. And then I go get a little bit more area. That would be the second value for my function, the third value for my function, and so on. So I slowly kind of go to the right as my x value increases. I'm slowly getting more and more of this area. All right, these are called accumulation functions because I'm slowly adding area as my x value increases. All right, we're not going to be too concerned about where these functions come from. We just have to kind of deal with them. But the fundamental theorem of calculus part 1 says if I take the derivative of this type of function, what's going to happen? Well, it turns out that the integral symbol and derivatives kind of cancel each other out. So when I try to take the derivative of all of this thing, these two things are going to cancel out. So basically this is going to cancel out with that, and I just get f of x. So really what's going to end up happening in practice is this x here just gets plugged in there. All right, so pretty simple in terms of the process we have to do. But remembering the theorem is the difficult part. All right, so find the derivative of this function g of x, which is an accumulation function because it's integral with 1 to x. All right, this should be a t because we're doing dt. All right, but when I do this derivative, g prime of x, it says all of this is going to basically cancel out, and I plug in x for t. All right, so that's all you have to do. If you know this theorem, then that's it. There's no real other work you have to do. You just know that the derivative and the integral symbol kind of cancel out, and we basically just get this as our answer. Now, what about this one? All right, this is an accumulation function, but there's one extra thing that makes this slightly more complicated, and this is in the top there, we have the square root of x instead of just an x. All right, so this is the same thing, but it's a chain rule problem. So the first part of my derivative is going to be just like before. I just plug that in. Just like before we put that x in, now we're going to put the square root of x in. But since it's a chain rule problem, now I multiply this by the derivative of whatever's up here, and the derivative of the square root of x is 1 over 2 squared of x. All right, and again, that's the whole problem, slightly more complicated than the last example because it's a chain rule problem, but really not too much calculation going on. You just plug in whatever's on the top in for t, and if it's more complicated, just do the chain rule. All right, so here's another one, another example. All right, so the first thing when I do the derivative is just take whatever's here and plug it in for t. I need cosine of x cubed, and I need to multiply that by the derivative of x cubed, and that's 3x squared. Again, that's the whole thing. Nothing else you have to do when you're finding the derivative of these accumulation functions. All right, here's where things get a little bit more complicated. All right, here we're trying to find this derivative. It's an accumulation function because we have that x up there. But here we also have the x on the bottom. And the fundamental theorem of calculus doesn't work unless there's a number down there. So here's what we have to do. We have to break this one up into two different integrals. So we had this rule early on when we were learning about integrals that if we have an integral from, say, a to b, instead of doing this full integral all at once, I could break it up into smaller chunks. So I could do it from a to c first, and then from c to b. So we're going to do something like that. We don't know what x and 2x are. So if I kind of think about them on a number line, I could have x here and 2x here. This is the actual kind of part of my integral I want. But I don't want it to start at a value. So the easiest value to start at is just put 0 somewhere. And I'm going to have two different areas. I'm going to have 0 to x and 0 to 2x. All right, so let's make those now. So I can say this is the same as the integral from 0 to x of t cubed dt. All right, and the integral from 0 to 2x of t cubed dt. All right, then what should happen? To get this is my kind of blue part of my number line, and this is the green part of my number line. How do I combine those two to actually get the red part? Well, I need these parts here to cancel out. So I need to subtract away this part. So it's going to be negative there and positive there. All right, so if I take away the negative part of this blue part, it'll cancel out with that part of the green part and just give me the actual part I want. All right, so this is where the fundamental theorem calculus can get a little bit more complicated, all right, when you have a number on the bottom and the top. But not for this, it's just the same. F prime of x. When I do derivatives, I just plug this number in. And so I'm going to have this negative sign that sticks around. For this one, I'm just going to have x cubed. The next one, the 2x is going to go in for t, so I'm going to have 2x cubed. I have to remember, since it wasn't just a single x up here, I have to multiply by its derivative, which is just 2. All right, so now we'll just do a little bit of simplifying. Negative x cubed. It's going to be 8x cubed times 2 is 16x cubed. My final answer is 15x cubed. All right, so this is kind of the limit of how difficult fundamental theorem part 1 problems can get, is when they're putting a bound on both parts of the accumulation function. But the process is always the same, basically starting them both at 0 and subtracting one of them and adding the other one so that your kind of areas make sense in your number line. And then when you're doing the fundamental theorem of calculus, just plugging that top thing in for your t's, and if you need to, doing the chain rule. All right, so a little complicated for this last example, but the basic idea, pretty simple, is that derivatives and integrals are going to cancel out, and you just plug in that x into your function. All right, so here's one for you to try on your own. All right, find the derivative of this function. All right, so hopefully you didn't think this one was more complicated than it was. All right, there's just an x down here. There's just a number down here. So this is the straight application of the fundamental theorem of calculus. You just take this x, plug it in for t, you're done. All right, so this is all you had to do for this problem.